All right, everyone, welcome back. Ready for another deep dive?
Absolutely, let's do it.
Today, we're tackling something that seems kind of simple on the surface, but trust me, it gets wild. We're talking files and file systems. And you know we love digging into listener suggestions, right?
Always.
Well, this one's been brewing for a while. Got a ton of you asking, what's the deal with files? They seem so basic. But, as usual, there's way more than meets the eye.
Yeah, I mean, we use files every single day. Click, drag, save, repeat. Right?
Exactly.
Yeah.
But have you ever stopped to think, what problem do files actually solve?
Well, they hold our stuff. Documents, pictures, all that.
True. But it's more than just storage, right? It's like, imagine if your kitchen was organized by just throwing all your ingredients, pots, pans, everything, into one giant drawer.
Oh, total chaos. I can't even imagine.
Exactly. Files bring order to our digital world. They're like those labeled containers in your pantry. And that's where file systems come in. They're the organizational whizzes behind the scenes.
It's the OS, the operating system, that actually uses the file system to manage all those files. Think of it as a massive, intricate filing cabinet for your computer. But the cool part is, you never have to see the mess inside.
Right. Like, I don't want to think about where each bit of data is physically stored on my hard drive.
And you don't have to. That's the beauty of abstraction. The file system handles all those messy details, whether your data is scattered across a spinning hard drive or stored on a flash memory chip. It presents this clean, organized view to you and your applications.
So I can picture the file system as this, like air traffic controller, making sure everything runs smoothly without me needing to know the routes of every single plane.
That's a great analogy. It's all about managing resources effectively behind the scenes.
And you mentioned applications. Does the way a file is structured, like how that data is organized inside, does that matter to them?
Oh, absolutely. It's like the difference between a neat stack of papers and a jumbled pile. Both technically contain information, but one is way easier to work with, right?
Makes sense. So tell us more about these different structures.
The most basic way to think about it is sequential access. Like reading a book, you start at the beginning and go to the end. But what if you need specific information quickly? That's where direct access comes in. Imagine having an index for that book, letting you jump straight to the page you need.
Like using a student ID number to pull up the specific student's record instantly. We saw that example in one of the articles you shared.
Exactly. That's a key field within a record-based file structure. Databases use this all the time. The file system provides these different access methods so programs can work with data efficiently.
Okay, that makes so much sense. Now let's talk about something that I find really cool: file types. Like, how does my computer know what to do with a file?
It's all about those subtle signals and hidden information. File types are like labels whispering to the operating system, hey, handle me this way. And the secret sauce is metadata.
Metadata, isn't that like data about the data? Sounds sneaky.
It is. And super useful. It's like a hidden instruction manual tucked inside each file. One of the most important pieces is the magic number.
Magic, okay, now you're just messing with me. What is that?
Think of it as a unique code snippet right at the start of the file. It's like a file's fingerprint. The OS reads this magic number instantly and knows, boom, this is an image or a document or an audio file, whatever it may be.
So that's why we have different file extensions like .docx, .jpg, all those little tags, right?
You got it. We see those extensions and they give us a clue, but honestly, they're more for us humans than for computers.
Really? So the computer isn't relying on those?
Nope. The OS relies on that much more precise magic number. Extensions can be easily changed, even accidentally, but that magic number is like a file's true identity.
Okay, mind blown. Who knew files were so complex? But here's a thought we're throwing more and more at our computers. Huge data sets, streaming services, all sorts of wild stuff. Could our current file systems handle a data explosion, or would we need to reinvent everything?
Now that's a question that keeps a lot of people up at night, including me. I think the future of file systems will be all about adaptability. Imagine systems that can restructure themselves on the fly, optimizing for how we're using the data. Or what about file systems designed with security and privacy at their core to combat those ever-present data breaches?
Whoa, those are some seriously next-level ideas. Well, listeners, there you have it. We dove into the seemingly mundane world of files and ended up contemplating the future of data itself. Thanks for joining us on this deep dive. Until next time.
All right, everybody, welcome back. It's time for another deep dive. You know, sometimes you just get curious about how things work, like what's going on behind the scenes.
I'm always down for a little behind-the-scenes action.
Well, today we are tackling something that's essential to our digital lives, but often overlooked: File directory structures.
Ah, the unsung heroes of our computers.
Exactly. We're talking about the hidden architecture that keeps your gigs upon gigs of data from turning into a chaotic mess.
It's like, imagine if you had every single book ever printed just piled up in a room with no organization whatsoever.
Total nightmare. But thankfully, our computers have systems for preventing that kind of digital chaos.
Right, and that's where file directory structures come in. They give all those ones and zeros a place to live.
So we've been digging into this fascinating technical paper on file systems. And right off the bat, it mentions tree-structured directory hierarchies.
The tree analogy, it's a classic for a reason.
It is. But can you break it down for us? What's the logic behind using this tree structure to organize files?
Well, think about it. Hierarchies are everywhere in the real world. It's all about organization and efficiency, right?
Makes sense.
Take a library. For example, you've got your fiction section, your nonfiction, history. And within those sections, you have even more specific categories.
Yeah, like within fiction, you might have mystery, sci-fi, romance.
Exactly. And that's basically what a tree structure does for your computer files.
Yeah.
Your main directory, that's like the library itself. Then you've got folders within folders, creating those branches, just like the specific sections in the library.
So it's like each file has its own little address in this giant digital library. And speaking of addresses, our source mentions absolute and relative path names. Are those just fancy ways of saying directions?
You got it. An absolute path name, it's like giving someone directions from a fixed point. Think of it like the North Star of your computer's file system. You'd say something like, okay, start at the hard drive, now go to the users folder, then find documents, and so on.
So very specific instructions. What about relative path names? Are those like the backroads shortcuts?
Kind of. It's all about context with relative path names. It's like saying, okay, from where you are right now, take 2 steps forward and then 1 step to the left.
I use those kinds of directions all the time. It's the big blue house, 3 doors down from the corner.
Right. It all depends on your starting point. So in your computer, a relative path name tells the computer how to find a file based on its location relative to the current file or directory.
It's okay, so we've got our files organized all nice and neat in their digital treehouse, but our source hints that sometimes you got to get a little bit more, let's say, creative with file organization.
Oh yeah, the tree structure is great, but it's not always enough. Files and folders can be kind of complicated.
That's where these directed acyclic graphs come into play, right?
Sure do. DAGs, for short.
DAGs. I gotta admit, that sounds a bit intimidating, like something out of a science fiction movie.
It's not as scary as it sounds, I promise. Think of it like, instead of a rigid tree, it's more like a web. Files can have multiple pathways leading to them.
Okay, so less like a family tree, more like a network. I kind of like that.
Right. And this whole network thing, it allows for something called links. These are like shortcuts within your file system. They point to the original file without actually creating a duplicate.
Wait, so instead of having the same file copied in multiple folders, you have one file and everyone just has a link that points to it.
Precisely.
Yeah.
It's a much smarter way to share files.
Mind blown. That's got to be a lifesaver for storage space, especially if you're dealing with massive files for video editing or something.
Oh, absolutely. And it makes collaboration way smoother. No more sending massive files back and forth.
Right. It's like everyone's working from the same playbook, so to speak, which is super important in a collaborative environment. So instead of my hard drive looking like a digital hoarder's paradise with a million copies of the same file, I can have one file neatly tucked away with a bunch of these links pointing to it. That's amazing.
It's a pretty ingenious system, right?
But it does make me wonder, how does the computer keep track of all these links? Like, how does it know not to delete a file if someone's still using it, even if it looks like it's just sitting there doing nothing?
That's where reference counts come in. They're like little counters for your files.
Counters. Okay, I'm intrigued. Tell me more.
So every file, every folder on your computer, it has this invisible reference count attached to it. And every time a new link is created that points to that file, the reference count goes up by 1.
So it's like a tally of how many links are connected to that file.
Exactly. And if someone decides they don't need a link anymore and they delete it, the reference count goes down by 1.
Okay, that's actually pretty straightforward. I was picturing something much more complicated. But I guess sometimes the simplest solutions are the best, right?
Absolutely. And this whole reference count thing, it's like a safety net. It prevents the computer from accidentally deleting a file that someone's still using, even if they're accessing it through a link.
It's like, hold on, computer. This file's still got a purpose.
Right. Think of it like a library book. If a book is checked out by multiple people, the library's not going to get rid of it, right? They're going to wait until everyone's done with it.
That's a great analogy. So the reference count is like the library's way of knowing how many people still have that book checked out.
Exactly. And just like a library needs a system for removing outdated books to make room for new ones, our computers have a way of dealing with those digital dust bunnies, those files that are no longer needed.
Oh, you mean like when I download a file and then completely forget about it? I'm guilty of that.
Happens to the best of us. But don't worry, your computer has a built-in cleanup crew for that. It's called garbage collection.
Garbage collection. Sounds efficient.
It is. Basically, it's a process that runs in the background, periodically scanning your system for files that have a reference count of 0.
So if a file's reference count hits 0, it's like, adios, amigo, you're out of here.
Yep. The garbage collector swoops in and frees up that space. It's all about optimizing storage and keeping things running smoothly.
Okay, that makes me feel a lot better about my messy digital habits. But speaking of digital organization, there's one more piece of the puzzle we got to talk about: symbolic links.
Ah, yes, symbolic links. They're like the cool kids on the block, with a few extra tricks up their sleeves.
Oh, from what I understand, they're like links, but with a twist.
That's a great way to put it. They both act as pointers, but how they interact with the file system, especially during deletion, that's where things get interesting.
All right, you've piqued my curiosity. Lay it on me what makes symbolic links so special. Okay, spill the tea. What's the deal with these symbolic links?
All right, so remember how we were talking about reference counts?
Mm-hmm.
And how deleting a regular link is basically like telling the computer, hey, one less person needs this file.
Right, right. It's like returning a library book.
Perfect analogy.
Mm-hmm.
Now, with symbolic links, it's a little different. They're more like, think of a shortcut on your desktop.
Okay, I'm picturing it. Let's say I've got a shortcut to my favorite photo editing program.
Right, so if you delete that shortcut, does it delete the actual program itself?
No way. That would be disastrous.
Exactly. You're just deleting the shortcut, not the actual program. And that's the key difference with symbolic links. They point to the original file, but deleting the symbolic link, it doesn't affect the original file's reference count at all.
Whoa, okay, so even if I delete a symbolic link, the file it was pointing to, it's still safe and sound somewhere on my hard drive.
You got it. It's still out there, living its best life. And this actually gives you a ton of flexibility because you can have multiple symbolic links scattered all over your file system, all pointing to that same file. And deleting one of those links won't accidentally nuke the original file.
That's really cool, but it also sounds like it could be a bit risky if you're not careful.
That's a great point. Because remember, symbolic links don't affect that reference count.
Yeah.
So you could end up deleting a file thinking it's no longer needed, but then boom, somewhere down the line, a program tries to use it and it's gone.
Yikes. That's a good argument for keeping your digital house tidy. But seriously, this has been fascinating. Who knew there was so much going on behind the scenes with our file directory structures? It's like we've uncovered this whole hidden world inside our computers.
It really is. It's amazing how much complexity is involved in something we use every single day but rarely think about.
Absolutely. So, big takeaways for our listeners today. File directory structures, they're the unsung heroes of our digital world. They keep our data organized, our computers humming along smoothly, and they allow for some pretty amazing things like sharing files without creating a million duplicates.
And it's not just about organization. Understanding those nuances, like the difference between regular links and symbolic links, that can save you from some serious headaches down the road.
Couldn't agree more. It's all about being informed and using your digital tools wisely, right?
Exactly. Knowledge is power, especially when it comes to navigating the digital world.
Well said. A huge thank you to our expert for taking us on this incredible deep dive. And to our listeners, as always, thank you for joining us. Until next time, keep those digital curiosity fires burning. Okay, so get this right. Imagine a library.
Okay.
But not just any library.
Mm-hmm.
This library, it's got billions and billions of items,
Yeah.
okay? And you need to find like one specific page, and you need it instantly.
Oh, wow.
That's kind of the scale that file systems are dealing with inside our computers every single day.
Yeah, that's a really good way to put it.
It's mind-blowing when you think about it.
It is. And the thing is, most people, they don't even realize just how much is going on behind the scenes every time they open a file or save a document.
Right, like it's just magic click and it's there.
Exactly. But it's not magic. It's all thanks to file systems.
File systems, the unsung heroes of our digital lives.
Seriously, I mean, think about it. Without a good file system, our computers would just be a jumbled mess of data, impossible to navigate.
Total chaos.
Exactly. A file system is what makes all that data make sense. It's what lets us actually find and use our files.
So it's kind of like, it's the difference between rummaging through a junk drawer versus like having a perfectly organized filing cabinet.
That's a great analogy. A file system is like having a system of folders and labels for your entire computer.
So instead of just having this massive digital junk drawer where everything's just thrown in haphazardly, a file system creates order.
Precisely. And that order is crucial for everything from how quickly we open a document to how much storage space we have left.
And it's all thanks to file systems.
That's right. I mean, it's not just about organization either. A good file system can actually speed up your computer's performance.
Okay, so we're talking about more than just digital neat freaks here.
Oh yeah, this is about making our computers work efficiently. And one of the ways they do that is by storing a ton of information about each file.
You mean like more than just the file name?
Way more. We're talking about hidden data, metadata, that tells the computer everything it needs to know about that file.
Metadata. Okay, so like what? Give me an example.
All right, so you've got your file, right? Let's say it's, I don't know, that picture of your cat wearing a party hat.
Obviously.
Now you see the file name, partycat.jpg, right?
Right.
But your computer sees so much more. It sees the file size, like how much storage space that adorable image is taking up on your hard drive.
Okay, that makes sense. Gotta keep track of that.
Exactly. And it also sees the file type, which in this case is .jpg.
So it knows it's an image?
Exactly. That little extension tells the computer how to handle the file. Like, it knows to open it with your photo viewer instead of, say, your music player.
Which would be weird.
Very weird. But it goes even deeper than that. Your computer also keeps track of the file's location.
Like where I saved it on my computer.
Well, kind of. But it's not just about what folder it's in. The file system keeps track of its physical location on your hard drive.
You mean like the actual spot on the hard drive where all those ones and zeros are stored?
You got it.
Yeah.
Think of it like every little bit of data has its own unique address on your hard drive. And the file system, it's like the master postman. It keeps track of all those addresses, so it knows exactly where to deliver and retrieve every single bit of data.
Wow, okay, so we're talking about a whole other level of organization here. It's not just about folders and files, it's like a whole city map of data.
That's a great way to think about it. It's like a super detailed map of your entire hard drive. And that map is essential for everything your computer does with those files.
So it's not just about where the file appears on my screen, it's about where it physically lives on the hard drive?
Precisely. And that physical location is a crucial piece of metadata.
So file size, file type, location, anything else hiding in this metadata treasure chest?
Oh, there's more. There's file protection, for one. This is how your computer knows who can access which files and what they can do with them.
Ah, so that's how it knows I can't mess with system files, but I can edit my own documents.
Exactly. It's like each file has its own little security detail, making sure only the right users have the right kind of access.
So it's like a digital security guards for our data.
That's a great way to put it. They're the gatekeepers of your files. Make sure everything stays safe and sound.
Okay, but these security guards, they gotta keep pretty detailed logs, right? Like, gotta know when a file was created, when it was last accessed, all that jazz.
You're on the right track. We're talking about timestamps. They're another crucial piece of metadata.
Timestamps, okay.
Yep. They tell the computer when a file was created, when it was last modified, when it was last opened, all that good stuff.
I guess that could be useful. Like if a file gets corrupted or something, you could maybe use the timestamps to recover an earlier version, right?
Exactly. Timestamps are a lifesaver for data recovery. They're also super helpful for backups because they tell the computer which files have changed recently and need to be backed up again.
So it's like having a built-in history log for every single file on your computer.
Precisely. And it's all thanks to those little timestamps tucked away in the metadata.
Okay, so we've got all this metadata, this hidden information, but how does the computer actually organize it all? We're talking about billions of files, each with its own set of data.
Right. It's like imagine if a library just kept a single list of every book they had, just one massive unsorted list.
That would be a nightmare to navigate.
Total chaos. Thankfully, that's not how file systems work. They use something called directories.
Directories, like folders.
Exactly. Folders are basically visual representations of directories. Think of directories as the organizational backbone of your file system.
Okay, so instead of just dumping every file into one giant digital room, we've got these directories, these folders, to keep things organized.
Exactly. And just like you might organize your physical files into folders and subfolders, your computer uses directories to create a hierarchical structure for all your data.
That makes sense. But how does that actually work on, like, a technical level? How does the computer keep track of all these directories and the files within them?
Well, one way to think about it is each directory has a list of entries.
Entries?
Yeah, like a card in a card catalog. And each entry contains information about a file stored within that directory.
Okay, I'm picturing this massive card catalog, each card representing a file.
Exactly. And on each card, you've got all the metadata we've been talking about. File name, size, type, location, all that good stuff. Now imagine you've got this giant card catalog, right?
Right.
And you need to store information about a whole bunch of files, each with a different file name. One way to do it is to give each card in the catalog a fixed length.
So, like, every card is the same size no matter how long or short the file name is?
Exactly. It's a simple system, easy to implement, but it can be a bit inefficient.
How so?
Well, what happens if a file name is longer than the space allotted on the card?
Oh, right. You'd have to, like, truncate the name or something.
Exactly. And then you run into problems like, what if two files have the same truncated name? It can get messy.
Okay, so fixed length entries aren't ideal. What's a better solution?
Well, a more flexible approach is to use variable length directory entries.
So the cards in our card catalog can now be different sizes.
Precisely. Each card can expand or contract to fit the file name perfectly so you don't waste any space.
That's much more efficient. But now I'm picturing this really messy card catalog with cards of all different sizes scattered everywhere.
And that's where clever space management comes in. One common approach is called coalescing.
Coalescing? Okay, that sounds intriguing.
So imagine you delete a file. That leaves the gap in your directory, right? Like a blank space where the card used to be.
Right.
Coalescing is basically like tidying up the card catalog. It merges those gaps together to create larger free spaces.
So it's like defragmenting your hard drive, but for directories?
That's a good way to put it.
Yeah.
Coalescing helps keep the directory compact and organized, even with variable length entries.
Okay, that makes sense. But managing all these different size entries, it still seems like it could get complicated.
It can, which is why some file systems use a different approach altogether. Pointers.
Pointers.
Yeah, pointers. Think of it like this. Instead of having the entire file name directly on the card, you have a pointer that tells the computer where to find the actual file name.
Okay, so it's like a reference, a link to where the full file name is stored.
Exactly. So the directory entry itself can be relatively small and consistent in size because it just contains the pointer and a few other essential bits of metadata.
And then the pointer, it's like a set of directions that tells the computer, hey, if you're looking for the full file name for this entry, go over there.
Precisely. It's like having a bookmark that takes you directly to the right page in a book. And here's the really cool part. If you rename a file, you often only need to change the pointer, not move the entire entry.
Oh, I see. So it's like changing the label on the bookmark without having to move it to a different page in the book.
Exactly.
Yeah.
It's a really elegant and efficient way to manage file names, especially if you're dealing with a lot of renaming and moving files around.
That's some serious organizational magic going on behind the scenes.
It is, and it highlights just how much thought goes into making file systems as efficient as possible.
So we've talked about how directories are organized, but what about actually finding files within those directories? I mean, it's not like my computer scans through every single file every time I hit search, right? It can't be, right? That would take forever.
You're exactly right. Searching through a massive unsorted directory, that would bring your computer to its knees. Imagine trying to find one specific book in a library, but you have to check every single book, one by one.
Yeah, that's not exactly efficient.
Not at all. That's why file systems use something called search algorithms. They're like the super speedy librarians of the digital world, able to pinpoint exactly what you're looking for without having to scan every single file.
Okay, so we've got our organized directories, thanks to those clever pointers we talked about. But we also need a way to navigate those directories crazy fast. That's where these algorithms come in.
That's it. Different file systems, they might use different search algorithms, each with its own pros and cons. But the goal is always the same, to find the right file as quickly as possible.
So how do they actually do that? What's the secret sauce?
Well, one common approach is to use an index. Think of it like this.
Okay.
You know how a library has a catalog, right?
Mm-hmm.
And the catalog is organized alphabetically by author or title.
Right, so you don't have to go shelf by shelf hunting for what you need.
Exactly. An index is like that catalog, but for your file system. It's a separate structure that contains information about where each file is located, but it's already sorted and optimized for searching.
So instead of rummaging through the entire library, the computer can just consult this super organized index.
Precisely. It's like having a shortcut to find exactly what you're looking for. And the best part is, file systems can have multiple indexes.
Multiple indexes, so like one for authors, one for titles, one for subjects, like that.
Yeah, exactly. You might have one index for file names, another for file types, and yet another for modification dates. That way, depending on what you're searching for, the computer can use the most efficient index for that particular search.
So it's like having a specialized librarian for every type of search.
Exactly. And the amazing thing is, all of this happens behind the scenes. We don't even realize how much complex organization and optimization is going on every time we open a file or search for a document.
It's kind of mind-blowing when you think about it, all that hidden complexity just to make our digital lives run smoothly.
It really is. It just goes to show how much thought and ingenuity goes into designing these systems that we often take for granted.
It's like a whole hidden world inside our computers, dedicated to keeping our data organized and accessible.
A world that most of us never even see.
Exactly. So next time you're zipping through files, remember those digital librarians working behind the scenes, making sure you find what you need in a flash.
To efficient file systems.
Cheers to that. And to another deep dive conquered. Until next time.
All right, so picture this. You download the latest blockbuster movie, excited to dive into some, popcorn-fueled cinematic goodness, and you double-click, the movie starts playing, and boom, you're in. Simple, right? But have you ever, stopped to wonder what kind of digital choreography makes that instant entertainment possible?
There really is something.
Well, today's deep dive throws open the curtain on that. The fascinating and often overlooked world of file systems. And trust me, it's way more exciting than it sounds. We're using this research you provided to really break down the fundamental operations that make your digital life, including that seamless movie streaming, possible. And to help us navigate this behind-the-scenes tour, we have an expert, someone who can explain even the most complex tech concepts with an ease that rivals that movie download speed.
You flatter me. But you're right, these systems are infinitely more fascinating once you peel back the interface. Imagine for a second a library. But instead of dusty tomes, it's filled with every byte of data that makes up your digital world. Videos, photos, documents, even that half-written email you're dreading. It's all there, meticulously organized. That's your file system in a nutshell.
Okay, I love that visual. A massive, meticulously organized digital library.
Yeah.
So every time we hit save, open, or delete, we're basically checking those digital books in and out.
Exactly. And just like a library has a system to keep track of its collection, your computer uses a file system to manage all that data.
Let's break it down then. Our sources lay out the core operations of a file system. We're talking about creating, destroying, opening, reading, writing, and manipulating files. It's like the language of file systems, right?
Precisely. These operations are the backbone of how we, or any program for that matter, interact with the file system. Whether you're clicking an icon or a program is running silently in the background, it all boils down to these fundamental actions.
So let's start with the birth of a file, that satisfying moment when we hit save. What magic is actually happening beneath that save button?
Imagine you're issuing a brand new library card, right down to the unique identification number. That's essentially your file control block, or FCB for short. Think of it as the file's ID card, holding crucial details about its identity.
So the FCB is more than just a name tag. What else is on this digital ID card?
Oh, it's a treasure trove of information. We're talking file size, creation date, permissions, all the metadata the system needs to manage that file effectively. You're basically placing this FCB, this meticulously crafted library card, into the catalog that's your directory under the file name.
Okay, that makes sense. The file gets its ID, its place in the library catalog. But what about when we decide it's time to hit delete? Are we dramatically tearing up that library card?
Essentially, deleting a file is like reversing the creation process. We take that FCB, our trusty library card, out of the catalog, freeing up that space on the shelves for new additions. This is where those disk blocks, the physical space where the data lived, are marked as available, ready for a new file to move in.
So it's not like the data is completely vaporized. It's more like putting those pages back on the shelf, ready to be used again.
A perfect analogy. The data might still linger for a bit, but the file system no longer recognizes it as a valid file. It's like the book is invisible until those pages are used for a new story.
Gotcha. Now let's move on to opening a file. Our research mentions this thing called the Open File Table, or OFT. It sounds very official.
Think of a bustling restaurant during the dinner rush. The kitchen needs a system to manage all those orders flying in, right? That's where the OFT comes in. It's like the restaurant's order system, meticulously tracking all the files currently being accessed by you or any program.
Okay, so the OFT is less intimidating, and more like an efficient head chef, making sure all those file requests are moving smoothly.
Precisely. And just like a well-run kitchen can get those delicious dishes out quickly, the OFT ensures speedy access to your files, which is particularly crucial for today's demanding operating systems. It's all about optimization.
This is making me hungry. But before I get sidetracked by those restaurant analogies, let's get back to our file system feast. We've got our menu, the OFT, tracking all the activity. But what happens when we actually click on a file, ready to dive into that content?
Great question. So you've picked your dish, or in this case, your file. But before you can dig in, there are a few things the system needs to check. First, it needs to make sure you have permission to access that file. It'd be a shame if anyone could just walk into the kitchen and grab an order, right?
Permission's right. Every file has those.
Yeah.
And once those are cleared,
Then it's all about getting you a table. Or, in our file system world, allocating an entry in the OFT specifically for that file. This is how the system keeps track of everything neatly.
and I'm guessing the kitchen better get a plate ready? Or is that where our trusty buffers come into play?
Spot on. Buffer allocation happens at this stage. These buffers are like temporary holding areas in the computer's memory, ready to receive those delectable bytes of data. Then, information about your order, all those juicy details from the FCB, gets copied to our OFT entry. And voila, the file is open and ready for you to consume.
Okay, this is way more intricate than I ever imagined. Who knew there were so many steps between clicking an icon and seeing a file open up? We're talking permission checks, table arrangements, buffer prep, all before we've even read a single word or watched a second of that movie.
It's a symphony of processes happening in milliseconds. But that's the beauty of a well-designed system that handles all this complexity so you can focus on what you actually want to do with that file.
Speaking of which, our sources mention this read-IMN instruction when it comes to actually reading a file. Care to demystify that for us?
Absolutely. Let's go back to that delicious meal analogy. You wouldn't try to cram the entire plate into your mouth at once, would you? You'd savor it one bite at a time. That's essentially what the read instruction is doing, taking a bite of data.
Okay, I'm following. So walk me through it. How does this bite-sized data consumption actually work?
Sure. The read instruction is like pointing to your specific order in the restaurant. Or in this case, the index in the OFT that tells the system which file you're currently enjoying. N is the size of your bite, the number of bytes you want to read at once.
So if N is the byte, then it must be where it ends up.
Precisely. M is the memory location, your mouth, where the data gets delivered. But just like we don't swallow before taking another bite, the system uses buffers to temporarily hold these chunks of data, ensuring everything flows smoothly. This is especially important when dealing with larger files.
Like when I'm streaming that movie. It wouldn't be very enjoyable if I had to download the entire thing before watching.
Exactly. Buffering allows you to start watching almost immediately, while the rest of the movie is discreetly being fetched in the background. It's all about that smooth, uninterrupted viewing experience.
This is mind-blowing. Okay, last movie analogy, I promise. Ever notice how you can effortlessly jump to any point in a song or video? Is there a file system explanation for that magic too?
You bet there is. That's the power of seeking. Imagine searching for a specific page in a physical book. You wouldn't flip through randomly, right? You'd use the index or table of contents to pinpoint that exact page number.
Right, because flipping through hundreds of pages would take forever. So how does the file system know where to go within that massive digital book?
It uses an instruction that looks something like this. Seek IK. You guessed it. It points to the specific open file in the OFT. The K is our target, the exact position, the page number within that file that we're after.
So the system does some lightning-fast math to figure out which block holds that data and where it starts within that block. It's like knowing the chapter and then scanning for a specific sentence on that page.
You've got it. It's all about precise, efficient navigation. Once the system locks on to that target, it can start reading the data from that point onwards. No more frustrating fast-forwarding or rewinding delays.
Seriously impressive stuff. But all good things, even that captivating movie marathon, must come to an end. So what happens when we hit that close button on a file? Are we slamming the book shut, or is there a more delicate process?
It's a bit more nuanced than a dramatic slam. Closing a file is more like carefully placing that book back on the shelf, making sure it's in the right spot. The system diligently saves any changes you made, updates the FCB to reflect those changes, and then releases that file's entry in the OFT.
So it's like checking the book back into the library, updating their records, and freeing up that table for the next eager reader.
Precisely. Closing a file might seem like a simple action, but it's an essential step in ensuring data integrity and freeing up those valuable system resources for the next task you throw at it.
It's amazing how much intricate detail goes into something. Like, as seemingly simple as just opening and closing a file, you know?
It really is. It highlights the incredible engineering behind these systems. Like,
It makes you realize that save button
yeah,
is more like a magical portal than just a simple command.
right. And speaking of magic, we haven't even touched on how files are manipulated. It's not just about creating, destroying, opening, reading, and closing.
Oh, right. Our sources did mention manipulating files. What falls under that umbrella? Is it as simple as it sounds?
Not quite. Think of all the things you might do with a file. Renaming it, moving it to a different folder, even duplicating it. These actions might seem straightforward, but under the hood, they often involve a carefully choreographed sequence of those core operations we've already discussed.
So renaming a file, it isn't just slapping a new label on it.
Not exactly. The system might actually create a copy with the new name, update the directory entry to point to that new file, and then quietly delete the old one. It's all about maintaining order and consistency within that massive digital library of yours.
Wow. Who knew there were so many secret operations happening behind the scenes? It's like the file system has its own little team of librarians working tirelessly to keep everything running smoothly.
That's a great way to think about it. And this intricate dance of operations becomes even more impressive when you consider the sheer volume of data most of us handle these days.
It's true. Photos, videos, documents. Our digital libraries are exploding. It makes you wonder, are there limitations to how much these systems can handle?
That's the million-dollar question. As we generate more and more data, file systems need to evolve to keep pace. We're talking about optimizing for speed, efficiency, and security on an entirely different scale.
That's a great point. It's like needing to invent a whole new system for organizing a library the size of a small country.
Exactly. It's a fascinating challenge for computer scientists. And for those of us who might not be coding those solutions, it's still incredibly beneficial to have a basic grasp of these fundamental concepts.
Absolutely. It not only deepens our understanding of the technology we use every day,
Yeah.
but also helps us appreciate the invisible forces that make our digital lives possible.
Well said. And on that note, I think we've successfully navigated the intricate and surprisingly fascinating world of file system operations.
We have. We've journeyed from the birth of a file to its eventual closing, uncovering the hidden language of creates, destroys, opens, reads, writes, and even those sneaky manipulations along the way.
We've explored the crucial role of the FCB, that all-important file ID card, and the OFT, our efficient restaurant order system for managing file access.
And we even dabbled in a few food analogies, to keep our brains fueled along the way. Thanks for joining us on this deep dive into the often overlooked world of file systems. It's definitely given me a newfound appreciation for the digital gears that keep our lives spinning.
Absolutely. The next time you open a file or hit that save button, take a moment to appreciate the intricate ballet happening beneath the surface. It's a hidden world of complexity, efficiency, and yes, even a touch of magic. Welcome to another deep dive, where we like to get into the nitty-gritty of things. You know, the stuff that makes you sound really smart when you're at a party or something. Today, we're going deep into the world of file systems. Like, ever wonder how your computer keeps track of all those photos and documents and cat videos? It's actually way more organized than you might think.
Oh, yeah.
Yeah, so we're going to be focusing on something called disk block allocation. And before you completely tune out, this isn't just some dry technical jargon. Understanding how your computer organizes this data on a hard drive can actually help you see why. Things slow down over time and maybe even give you some clues about how to keep your computer running smoother. So think of your hard drive as this giant library, right? With each disk block as a shelf where you store books, or in this case, pieces of your files. Now, how we choose to arrange those books on the shelves, that's disk block allocation. And believe it or not, the method we use, it has a huge impact on how quickly you can find that recipe for triple chocolate cake when you need it.
That's right. Just like in a library, there are different ways to organize things. Each one has its own advantages and disadvantages.
Okay, so let's start with the most straightforward approach. Contiguous allocation. So imagine storing a file in consecutive blocks, one after the other. Easy to find, right? Like having all the cookbooks line up on a single shelf.
Exactly. Contiguous allocation makes accessing files incredibly fast, especially if you're reading them sequentially from beginning to end. It's like just flipping through the pages of a cookbook, nice, smooth, and efficient.
Okay, but I'm kind of sensing a but here. There's always a trade-off, isn't there? I mean, this is file systems we're talking about, not some utopian data paradise.
You're catching on quickly. You're right. The problem with contiguous allocation is fragmentation. Over time, as you add and delete files of different sizes, you inevitably end up with gaps between the files on your hard drive. Imagine someone pulled out a few cookbooks from the middle of your shelf, and it leaves these empty spaces. Now try to fit like a giant multi-volume baking encyclopedia in there.
Ouch. Yeah, that's not going to be easy. So fragmentation basically means that there's plenty of space, it's just all chopped up, which makes it really hard to store new, larger files efficiently.
Exactly. And that's where other methods like linked allocation come into play. Instead of forcing files to be stored contiguously, they allow for a more flexible approach. Think of it like scattering those cookbook chapters throughout the library and leaving little notes in each one, guiding you to the next part of the recipe.
Oh, okay, so it's a bit like a treasure hunt for your data, with each block pointing to the next one in the chain? That sounds pretty clever, but I'm guessing it has its downsides too, right? I mean, following all those clues can't be as efficient as just grabbing the whole cookbook off the shelf, right?
You're absolutely right. While linked allocation solves that fragmentation problem, it definitely comes at the cost of performance, particularly when it comes to accessing a file sequentially. Imagine having to run all over the library following those notes just to read a single recipe from start to finish.
Yeah, and what about if you wanted to go directly to a specific page or section? I mean, that was easy with contiguous allocation.
Yeah, that becomes a lot trickier with linked allocation. You can't just jump to a specific point in the file. You have to start at the beginning of the chain and follow each link until you get to the block that you want. This is where we encounter the concept of seek time, which is basically the time it takes for the hard drive's read-write head to physically move to the correct location on the disk. And so the more scattered those blocks are, the more seeking is required. That makes the access slower.
Ah, so there's that trade-off again, flexibility versus speed.
Oh.
And I imagine all those little notes linking the blocks together, they take up space too, don't they? It's like sacrificing shelf space for breadcrumbs.
Absolutely. Those pointers, that's what they're called, they add overhead to each block, which means you ultimately have less space available for the actual data that you're trying to store.
Wow, this is so fascinating. This constant struggle for balance, it's like trying to find the perfect organizational system for a library that's constantly evolving and changing. So is there any way to like combine the best of both worlds, to kind of have our cake and eat it too?
Well, that's where clustered allocation comes in. Imagine grouping several blocks together to form a cluster.
Yeah.
And instead of linking individual blocks, we just link these clusters. This helps reduce the overhead from all those pointers and mitigate some of that fragmentation we talked about.
So it's kind of like organizing those scattered cookbook chapters into multiple volumes. That sounds like a pretty good compromise.
It is, but like all compromises, it has its limitations.
All right, lay it on me. I'm starting to think there's no such thing as a perfect file system, just clever workarounds for the inherent challenges of managing data.
You're absolutely right. With clustered allocation, even though we've reduced the number of pointers and made file expansion a bit easier, sequential access can still be slower compared to that contiguous allocation we talked about earlier.
Right, because we're still jumping between clusters, so those pesky seek times are still there.
Exactly. Plus, fragmentation, while less of an issue, can still happen if a cluster gets full, and there are no other free clusters near it that are available.
So cluster allocation, it's like this middle ground, but it's still a balancing act. It's just fascinating how much complexity is baked into something as seemingly simple as storing files.
It really is. And that's honestly just the tip of the iceberg.
Yeah.
There are even more nuanced approaches, each with their own advantages and disadvantages.
Well, this deep dive is just getting started. We'll be back soon to explore more of these fascinating file system strategies, including the intriguing world of the file allocation table, or FAT. Don't worry, we'll explain it all in plain English, no technical jargon required.
Welcome back to the deep dive. Last time, we left off talking about clustered allocation.
Yeah.
You know, that valiant attempt to strike a balance in the crazy world of file systems?
Right, because it seems like every solution we talk about has its own set of trade-offs. It's kind of like trying to pick the perfect food, you know? Some are juicy, some are crunchy, but like none of them are perfect in every single way.
I like that. That's a great analogy. And speaking of clever solutions, let's move on to a different approach. The file allocation table, or FAT.
The FAT, okay. I've definitely heard of this one, but I'll be honest. The name doesn't really tell me a whole lot. It's not exactly as intuitive as, say, linked allocation.
Yeah, you're right. It's definitely not the most descriptive name. But the concept itself is actually quite clever. Remember how linked allocation used those pointers scattered throughout the disk to connect all the pieces of a file?
Right, like little breadcrumbs.
Exactly. Well, FAT takes a different approach. Instead of embedding those pointers within the actual data blocks themselves, It keeps track of them all in a separate table.
Oh, interesting. So it's like having this master index for your whole hard drive, a single place to look up where all the pieces of a file are located.
Exactly, you got it. Think of it like a library catalog. If you want to find a specific book, you don't just wander the aisles aimlessly hoping you'll stumble across it.
Right. You go to the catalog and it tells you exactly where to find it.
Exactly. The FAT serves basically the same purpose for your computer.
That sounds way more efficient than just chasing those little pointers all over the disk.
It is. It definitely can be. And here's where it gets even more interesting. That FAT is typically small enough that it can actually be stored in the computer's RAM.
Really?
Which, if you remember, is much faster to access than the hard drive itself.
Oh, right. Because it's like RAM is like having a copy of that library catalog open right on your desk. You don't have to keep going back to the card catalog every time you need a new book.
Precisely. And this makes both sequential and direct access a lot faster compared to that traditional linked allocation. The computer can just consult the FA in RAM to find the next block that it needs, without having to wait for the hard drive to spin up or the read-write head to physically move to the correct location.
Okay, I'm starting to see why people like the FAT system. It's kind of like having a shortcut to finding all your data. But knowing how this works, I'm also starting to suspect that even this clever system probably has some drawbacks, right? I mean, nothing's perfect in the world of file systems, is it?
You're right about that. The FAT system definitely offers a good balance of efficiency and flexibility, but it does have limitations. One challenge is that as the storage capacity increases, that FA table, it can get really big. And a bigger table obviously means that it takes more time to search for the right entry, which could potentially negate some of those speed benefits we were talking about.
So it's that classic trade-off again
Yeah.
between having this comprehensive, detailed index, but also needing to make sure that it's manageable in size.
Exactly. And while the FAT does a pretty good job of mitigating fragmentation compared to the linked allocation we talked about,
Yeah.
it doesn't completely eliminate it. As files are added and deleted and resize those entries in the FA table, they can get kind of scattered around, which leads to, less organized allocation map.
So even with this clever catalog system, the FAT can't totally escape the chaos of a constantly changing library of data.
Unfortunately not. But all that being said, despite its limitations, the FAT file systems has actually been incredibly successful.
Yeah.
I mean, it was widely used in a lot of those early operating systems. And you know what? It's still used today for certain applications.
Really? Wow, that's actually really impressive for a system with such a, shall we say, unassuming name.
I know, right? It just goes to show that sometimes the simplest solutions can be the most effective. But the quest for even better file systems, it never really ends, does it?
That's right, the search for the perfect system continues. And speaking of quests, we've got another intriguing approach to discuss: indexed allocation. Welcome back to the deep dive. We're going to wrap up our little file system adventure here with a look at indexed allocation. It sounds like we're moving up from those simple catalogs to something a little more sophisticated.
That's a great way to put it.
Yeah.
Yeah, you can think of indexed allocation as like giving each file its own little personalized Dewey Decimal System.
Okay, now that's an analogy I can get behind. So
Mhm.
instead of one giant FAT table, each file gets its own little mini index.
Exactly. Each file gets what we call an index block, which is essentially a table of contents
Right.
that points to all the other blocks where that file's data is stored. And it doesn't matter where those blocks are on the disk, the index keeps track of it all.
So if I need to access page 50 of my digital baking encyclopedia, I don't have to scroll through all the pages leading up to it. I can just check the index and jump right there.
Exactly. That's the beauty of it. That's why indexed allocation is so great for both sequential A&D direct access. You need to read the whole file. No problem. That index guides you smoothly from block to block. You need to jump to a specific section. Boom. The index tells you exactly where to go.
This sounds almost too good to be true, honestly. Are there any downsides to this, this personalized index system? What's the catch?
Well, there's always a catch, right? One challenge with indexed allocation is figuring out how big to make that index block in the first place. If it's too small, you limit how big the file can actually grow. But if you make it too big, then you're wasting space that could be used for storing your actual data.
Ugh, there it is. That classic balancing act. How do they get around that?
So one clever solution is to use something called a multi-level index. Think of it like a hierarchical index that you might see in a massive textbook, right? You might have one index for all the chapters, and then within each chapter, there's another index for different subtopics, and so on. And this way, you can handle both really small files and these gigantic, massive files efficiently.
So a multi-level index, it's like having a map to your map, right? No matter how big that data gets, you can still find what you need super fast.
Exactly. It's all about optimizing that system for both speed and efficiency. But even with all of these really clever allocation strategies we've been talking about, there's one other crucial aspect of file systems that we haven't really touched on yet. Managing that free space.
Oh, right, of course. Because knowing where to put data is only half the battle, right? We also need to keep track of all those empty shelves in our data library, so they're ready for new information to come in.
Exactly. And that's where techniques like the bitmap come in.
Right, we talked about the bitmap a little bit earlier. It's basically like a map that shows you at a glance which blocks are free and which ones are already occupied.
You got it. Think of it like a giant chessboard.
Okay.
And each square on that chessboard is a block. And that bitmap will tell you instantly whether that block is free or if it's already being used.
So instead of wandering around a library hoping to stumble upon an empty shelf, the operating system can just consult this bitmap and instantly see where there's space to store new data.
You got it. Super simple, but really elegant solution for keeping track of all that available space.
And with that, I think we've covered the major players in the world of disk block allocation.
Wow, we've covered a lot of ground in this deep dive. From that simplicity of contiguous allocation to the flexibility of linked allocation, the clever indexing of FAT, and then that multi-level sophistication of indexed allocation, it's amazing to see how much ingenuity goes into something that most people probably never even think about.
It really is. And these systems are working constantly behind the scenes, just making sure that our digital lives run smoothly.
I know, it's crazy. I think the next time I save a file, I'm going to be picturing all these allocation methods in action.
Yeah.
It's like this beautifully choreographed dance of data happening on my hard drive.
I know, me too. It's fascinating. And on that note, we're going to leave you to ponder the hidden wonders of file systems. What kind of allocation method do you think your computer is using right now? Are you a FAT fan or an indexing enthusiast? A little research might surprise you. Until next time, keep exploring, keep learning, and keep those hard drives humming. Okay, ever hit that point where you're just staring at a loading screen thinking, come on, computer, it's just a file, not a rocket launch?
Yeah.
We've all been there. But what if I told you there's this sneaky trick operating systems use to make file access feel as fast as thinking? Today, we're diving deep into the world of memory-mapped files, your shortcut to turbocharged file handling.
And to really appreciate just how elegantly this solves the problem, it helps to remember how clunky traditional file access can be. Think about it. Every time you open a file, read some data, or need to save your work, you're essentially asking the operating system to play messenger between your application and the hard drive.
Right, like sending little notes back and forth.
Exactly. Every interaction involves these things called system calls, which are like formal requests, and those take time to process. And then on top of that, if the data you need isn't readily available in memory, the operating system has to go fetch it from the hard drive, which
can take forever.
Yeah, an eternity in computer time, right?
Okay, so enter memory-mapped files, our heroes in this story. Let's unpack how they work their magic.
Imagine this. Instead of all of that copying back and forth, the operating system creates a direct link between the file on your hard drive and a specific portion of your RAM.
So it's like creating a shortcut.
It's like setting up a portal. So accessing that file is no longer a long-distance call. It becomes like a local coffee chat.
So it's like the operating system says, look, I've got this file mapped in memory for you. Just reach in and grab what you need. No need for all that formal request nonsense.
Precisely. And here's where demand paging comes into play. Remember that the operating system is smart about how it manages memory. It doesn't load the entire file into RAM right away. Instead, it uses this clever on-demand approach.
It's all about efficiency. So the first time you try to access a part of the memory-mapped file, it's like, how do I put this? It's like ringing a doorbell.
Okay, I like that.
The operating system is like, oh, you need this specific part. Let me fetch it from the hard drive and load it into a convenient spot in memory. But here's the real kicker.
Once that part of the file is in memory, anytime you need after that is lightning fast. The operating system doesn't need to bother with those system calls or disk reads anymore. It just becomes a simple memory operation, like accessing any other data that's already loaded in your RAM.
And that, my friend, is the secret sauce. It's not about loading the entire file into RAM, which would be a huge waste of space. It's about strategically loading the bits you need when you need them. Talk about efficient.
Exactly. This is one of those elegant solutions where the aha moment is all about understanding just how much unnecessary work is being avoided.
But hold on, there's a bit of a head scratcher here. If I make changes to a memory-mapped file, does that mean it's instantly saved to my hard drive? Because I'm used to things like auto-save features that work in the background.
Ah, good question.
So, are my changes being saved in real time, or is there some sort of delayed gratification going on here?
Well, it's not quite instant. Think of it this way. Imagine you're sketching out ideas on a whiteboard.
Okay.
You don't erase and redraw every single time you make a slight adjustment, right? You make those quick changes in the moment, and then later on, you might decide to make things more permanent.
Okay, so the operating system is like, hold your horses, I'll get to saving those changes when I have a moment to spare.
Precisely. The operating system keeps track of those modifications you made in memory, and it will eventually write them to the physical disk. It just might not happen instantaneously. It's more like a strategic batch update.
Interesting. It's like the OS is prioritizing speed and efficiency, saying, I'll handle the disk writing later when I'm not so busy juggling everything else.
Exactly. And just like, different artists have their preferred ways of working with a whiteboard, different operating systems might have slightly different approaches to managing these updates. But that core idea remains consistent. Leverage memory for speed and streamline those disk operations.
Speaking of different operating systems, I came across a fascinating tidbit about Solaris while we were prepping for this deep dive. Did you know that Solaris, which is a type of Unix, takes this whole memory mapping concept to a whole new level?
Oh, absolutely. Solaris is known for its efficiency, and its approach to memory-mapped files is a prime example of that.
It turns out Solaris treats essentially all file input and output as memory mapped.
Wow, really?
Yeah, whether the user explicitly requests it or not, it's like they said, you know what, this whole memory mapping thing works so well, let's just make it the default.
It's a bold approach, and it highlights a really crucial advantage of memory-mapped files: their ability to facilitate shared memory. Because, you see, it's not just about making one process faster, it's about enabling multiple processes to access and potentially even modify the same data at the same time, all without those clunky, old-school communication methods.
Hold on, multiple processes messing around with the same file at the same time? That sounds like a recipe for disaster. How does that even work without things getting totally out of sync?
It all comes down to the magic of virtual memory. Remember how each process gets its own virtual address space, which the operating system then maps to physical memory?
Yeah, it's like each process gets its own little sandbox to play in.
Exactly. With memory-mapped files, the operating system can very cleverly map the virtual memory spaces of different processes to the same physical location where that shared file data resides.
So it's like giving those different processes windows into the same room. They can all see and interact with the same information.
A perfect analogy. And if you're looking for a visual representation of this, figure 10.6.1 from the source material does a great job illustrating this concept. It shows how each process has its own virtual memory space, but they can all be mapped to the same physical memory address where that shared file lives.
Okay, that makes sense. But I have to ask, if multiple processes can write to this shared memory, wouldn't that create chaos? What happens if two processes try to modify the same piece of data at the exact same time?
That's where things get even more interesting. The operating system has a few tricks up its sleeve to prevent those sorts of conflicts. One of those tricks is a very clever mechanism called copy on write.
Copy on write. That sounds intriguing. Tell me more.
So with copy on write, imagine you've got these two processes happily sharing a memory mapped file.
Okay, yeah.
They're both reading data, everything is peaceful. But then one process decides, you know what? It's time for me to make a change. Now, instead of just letting it directly modify that shared memory, which could lead to all sorts of confusion and conflicts, the operating system steps in and says, hold up a minute.
Like a digital bouncer, right? Let's keep things orderly in here.
Exactly. So the operating system creates a private copy of that specific portion of the memory mapped file just for that process that wants to do the writing.
Ah, so it's like giving that process its own little private whiteboard to scribble on.
Exactly. And the other processes don't even realize anything has changed. They're still looking at the original untouched data.
Okay, that's pretty clever. So it prevents any sort of accidental overwrites or anything like that, it sounds like?
Precisely. It ensures that even when changes are being made, other processes continue to see a consistent view of the data, prevents all sorts of unintended consequences, all about maintaining order in the midst of these shared resources.
The operating system is like a super efficient project manager, making sure everyone has the right version of the document and preventing any collaborative chaos.
Now, to bring this all back down to earth a bit, the source material provided a really neat example using the Windows API. I think it'll help solidify how we actually use memory-mapped files in the real world.
All right, let's fire up those code snippets. I always find concrete examples make things click a lot better.
Absolutely. So in the Windows world, we have functions like create file mapping and map view file. They might sound a bit intimidating at first, but they're really just the tools of the trade.
Okay. So create file mapping, is that like setting up the shared memory space in the first place?
Exactly. Think of it as drawing that initial outline on the whiteboard. It's the function that establishes that crucial connection between a file on your hard drive and a region of virtual memory.
Got it. Laying the groundwork for collaboration. And what about map view a file? What role does that play?
That's where a process steps up to the whiteboard, ready to contribute. Map view O file is how a process creates a view of that matched file that we just talked about within its own little virtual memory world.
Makes sense. So it's like claiming a section of the whiteboard to start jotting down ideas.
Precisely. It's all about giving processes their own access to that shared space.
Now, the example also mentions this thing called a named shared memory object. Is that just a fancy way of saying the file? Or is there something more to it?
That's a great question. It's a bit more nuanced than simply referring to the file itself. This named shared memory object, it acts like a shared label, or kind of like a meeting point. It's a way for different processes, maybe even ones from different developers, to find and connect to that same memory-mapped region without needing to know all the low-level nitty-gritty details.
So it's like putting a big sign on the whiteboard that says project brainstorming, so everyone knows they're in the right place.
Exactly. Clear communication, coordination, that's what it's all about in the world of shared memory.
Now, the example goes on to show a producer process writing a message to this shared memory, and then a consumer process reading it. It's like a digital relay race.
Precisely. This producer-consumer pattern, it's a classic illustration of how memory-mapped files can facilitate seamless communication between different processes.
And the beauty is there's no need for all that complicated message passing or constant back and forth, right? They just have this direct line of communication through the shared memory.
Exactly. And this pattern isn't just some theoretical concept either. This is used in a wide range of real-world applications. I mean, we're talking everything from high-performance databases to, those real-time streaming services we all use.
Oh, wow, okay.
They're behind the scenes there too.
So that lag we were complaining about at the beginning of the episode, memory-mapped files could be working behind the scenes in those scenarios to speed things up.
You got it. They're like the unsung heroes of smooth, speedy data handling. And if you're interested in actually seeing this in action, the source material even mentions a programming exercise where you can build your own, well, a simple version, of course, but a producer-consumer system using memory-mapped files.
Now that's tempting, but we might have to save that coding adventure for another time.
Agreed. But before we wrap up our deep dive into the world of memory-mapped files, it's worth acknowledging that, like any powerful tool, they do come with certain considerations.
Right, there's always a trade-off. What are some of the potential downsides or challenges that we should keep in mind?
Well, one of the key ones is definitely data inconsistency. If you have multiple processes writing to that same memory map region at the same time, without any sort of, synchronization, things can get messy. It's like having too many cooks in the kitchen, or, well, in our whiteboard analogy, it's like having multiple people trying to write on that whiteboard at the same time. Without some ground rules, you're bound to end up with a jumbled mess.
So it's all about making sure everyone plays by the rules, coordinates their actions when they're accessing that shared data.
Exactly. It's crucial to implement proper synchronization mechanisms to prevent data corruption and ensure that everything remains consistent.
It sounds like memory-mapped files are this fascinating example of how operating systems can bridge the gap between our computer's hardware and the software we use every day. We've seen how they can really turbocharge file access, enable this seamless communication between different processes, and even introduce some interesting challenges when it comes to data consistency.
Indeed, and for me, memory-mapped files are a real testament to the ingenuity of operating system design. Finding these elegant solutions to complex problems, it's really quite impressive. And with that, we'll leave you to ponder this final thought. What other creative applications of memory-mapped files can you envision?
Keep those creative juices flowing, and we'll catch you in the next deep dive.